So, hello everybody. I think it's time to start. And I'm really proud to talk today in the audience full of exciting engineers and exciting people. And today I want to talk to you about accessing remote data and dealing with this data, living with it, and staying sane at the same time. And as far as I've got already a few questions, despite the title that you can see on this slide, I'm not going to talk too much about Haxl library itself. I'll just describe you the idea and the motivation behind this library. But 99% of my talk will be about Clojure, not about Haxl, so there's nothing to worry about. And by the way, I shared a link to my slides on Twitter, so you are welcome to follow me from your laptops if you can't read from this screen for any reason. A few words about myself. My name is Alex. I'm CTO at Identify company. And to be more clean on this point, I'm almost all-day coding kind of CTO, which is usual situation for startups. And we are a San Francisco-based startup. And the platform that we built empowers thousands of event organizers to create own private social networking applications that boost engagement during the event, that catalyze learning, and help sponsors to connect to the attendees during the event. We've been using Clojure and Clojure script for years already, and I'll be proud to make another talk someday just to share all experience and all knowledge that we've got so far. But today I want to draw your attention to a single problem that we are facing all the time in our day-to-day job. You can see here the simplest agenda ever possible. Please don't miss third point. And I'm going to leave like 5, maybe 7 minutes at the end of my talk for a short Q&A session, so you'll be able to answer all your questions. This is a screenshot from a private social network application, actually one of 1,000 applications that we currently run. And you can see here, what you can see here is a timeline. And most probably you saw such timelines before. For example, if you use such tools like Facebook or Twitter, and I believe you do. What you definitely can't see on this picture, how complex the underlying layer of data is. And what is timeline? It's a sequence of posts or some photos with some payload, like text, title, URL, photo URL, and with different information attached to it. For example, profile information, mentions, likes, comments, replies, prefetched information for URL that was shared, inappropriate claims, spam detection notes, your personal notes, your friendship status, and so on. So it's a huge graph of different pieces of data and different sort of connections between these pieces, right? And to collect all of this information, for example, to render this timeline on mobile device or inside our internal management panel, we have to talk to different data storages and to multiple backends at the same time. For example, we use React database as our main database for social content, for posts, likes, comments, and user profiles, and so on. We use Redis pretty heavily as our main cache layer, and in order to keep track of all users' activity to calculate special activity score for each user. And we also use Postgres, not that much in those cases where we need strong consistency guarantees. We store their application settings and different kind of meta information that helps us to understand what your own application should look like and how it should behave in different situations. So let me be true developer and stop talking on this point and show you some code, right? And I assume that we already have these low-level primitives like fetch item and fetch collection all already implemented for us. And I assume that we using blocking calls, blocking HTTP request. This is almost the all code that you need, right? Here you can see timeline post main function at the end of the slide, which takes username and performs different steps of data fetching. It fetched timeline IDs calling to our microservice. By the way, I should also mention that we use microservice architecture, and so there are many small servers that we should talk to. Then we will take 20 IDs from this list, and for each ID in sequence, we will apply this fetch post procedure. And what fetch post will do, it will fetch underlying payload. It will find inside this payload ID for those users who wrote this post, and it will merge this information together. The same goes for fetching user. You can see there that we are fetching payload for user profile, and we're fetching some kind of score, activity score. So you can see that this code, it's really clean. It's concise. You can write it in a few minutes, I believe, and you can read it. You can see here all pieces of data that we need and all connection between these pieces. So we've done, right? There's no more dragons left to slay, right? And for sure, no. And there are a few drawbacks, and there are a few problems that we should deal with somehow. The first problem is obvious for you, right? This code is clean, but it will run very slowly because of these sequential HTTP calls, and to fetch next post, we should wait between previous fetches is done, which is very slow. The next problem that enumerated here is not that obvious from the code itself, but you can imagine a situation when you have, like, for example, some crazy friend, and most of your post in your timeline is written by this person, by this guy. And in this case, what will you do? You will fetch 20 posts with the same author, and then you will fetch the same user 20 times, because this fetch post and fetch user operation doesn't have any notion about sequential procedure at the bottom of the slide. So this work is really redundant, and we want to skip it somehow. And the next part, for example, if you use Redis, you should know that it supports this multi-get request and any kind of batching. You can put few intents to get different pieces of data into a single request, send it over network, and get all results back to you. It's really amazing approach how to reduce latency. And in this code, it's hard to use this approach, right? Not that hard. Let's try to do this manually. And this is a re-implemented version of the same piece of code that uses core.async package to send the request simultaneously, and some pieces of manual deduplication logic. And I'm not sure that you can read this code, and this is perfectly fine. There's nothing to worry about, because the entire idea of this slide is just to show you how many lines of code do you need to optimize previous fetch version. And this is not the root of the problem, right? Number of lines of code, we can deal with it. We can live with a huge code base if we need to. The main problem here that this code is all about efficiency. It's really hard to see what do you want to do behind how do you do this, behind all these low-level details about deduplication logic and async request and so on. So this means for us that optimization leads to unnecessary complexity in your code. And you can see this complexity on my slide. Further, I will show you that this is unnecessary complexity and we can avoid it. It's really hard to dig through the code and understand their data itself and connection between different pieces of data. And the biggest challenge here, this is not only a Clojure problem, right? There is nothing to do with Clojure in particular. We can switch to another language and problem stays. And if it's not a Clojure problem, let's explore the space and let's ask, are there some sort of solutions that was built in different languages or in other ecosystems? And yes, there are a few. There is this amazing paper, There Is No Fork. It was written by co-author of Haxl compiler. And I'm not sure what language it's written in English or in Haxl, but you can read it. There is a library that was described in this paper, Haxl. This is Facebook. This is Haxl library that was built in Facebook, and it's open source. You can find it on GitHub. It's really popular. And the key idea of this library to use applicative functors to manage all dependency between data fetches under the hood with implicit concurrency and implicit batching of all requests when it's applicable. And there is another library, Stitch. This is Scala library, and this is actually a part of internal Twitter infrastructure. It's not open sourced yet, maybe. I'm not sure about concrete plans on this. The key idea of this library is to build declarative abstract syntax tree of all data fetch operations, and then take special interpreter and that will choose the most efficient evaluation strategy. And actually, these ideas should sound familiar in this audience. And not only in this audience, but for Clojure community in general, because Go macro from core.async package uses just the same approach. It takes your code that looks like sequential code, and it recompiles it to some sort of state machine with a bunch of callbacks inside of it, and you don't see this. And most probably, you don't even need to know about this fact. At least until you'll get your first stack trace exception, but that's another story. And may we just steal this idea and to use it in Clojure code? And for sure, yes, why not? Quite common approach, stealing ideas. And today, I'm happy to introduce you library that I'm currently actively working on. It's called Muse, and you can find it on GitHub. It was open sourced like a couple of weeks ago and still in active development. It uses the same idea of building abstract syntax tree of all your operation, and it uses core.async package as an underlying abstraction to deal with concurrency. So this library aims to solve all problems that I just enumerated, and let me show you a few examples. Actually, I have a lot of them, but not that much time to talk about everything. So I will show you the key idea and key advantages of this library. So the main abstraction that library operates with is a data source. And what is a data source? It's an identifiable piece of remote data. And I am really sure that I don't need to talk in this audience what identity is and why identity is so important. I just want to draw your attention to a single fact. It's a realistic assumption. And right, if you have, like, for example, list of blog posts, you always have some sort of unique ID or unique URL or something that you can use to distinguish one post from another. And the second part of my definition is not that obvious. What is remote data? What does remote even means? And remote is about latency. Latency is about waiting. And waiting is actually doing nothing, which is pretty simple to do. And this is fundamental abstraction in software development world. As a backend engineer, I can, for example, think about my web server talking to my database over the network. And as a system-level engineer, I can, for example, think about my CPU talking to a memory. And we have here like different scales, but the same abstraction. And here I want to emphasize that Clojure future or promise is a wrong way to express the idea of latency because it's an abstraction of some sort of value that I will get in future. And I don't know how much does it cost for you to make this value for me. So there are two different situations. You can just sit there and wait for an external system to come back to you within a result, or you can run any kind of heavy computations. Two situations, and in general case, I don't have enough information to distinguish between the two, right? So I will use this helper, remote request helper, to show you how Muse library works. It just print your intent to send request somewhere, then emulate this latency. It's just wait for random number of milliseconds, and then it emulates receiving result from an external system. So remote data means that the time that I have to spend waiting for an external system is more than time that I will do some useful computations, something meaningful. For example, when I'm talking to my React database, I will spend much long. I will wait much longer for a response from React than I will, for example, decode byte streams with JSON in it into Clojure data structure. And this means for me that the data that stored in React is remote for me. So let's describe our first data source, speaker. And as you can see here, speaker has an ID, a name, and a topic, and number of slides in his presentation. So to do this, to describe data source, I use this data source protocol with a single function fetch. And as far as I use ID in my def record definition, I don't need to care anymore about identity. Muse will understand what I want to do. And what I really should care about is latency. And to deal with it, Muse library requires my fetch function to return core.async channel. I mean, return it immediately. And it will wait that someone, somehow, you will push the result of this fetch into this channel, eventually. So what's next? Muse library exposes this fmap function, which basically means I want this function name to be applied to the piece of data speaker when it's ready. And it actually does nothing right away, no computation, no data fetches. It's just declaration of my intent, what I want to do. And this is not a data source in full meaning, but it's some kind of data source because, I mean, the result of fmap function. Because obviously, if I have to wait before I'll get speaker, then obviously I have to wait before I can calculate the name of the speaker. And which means that the result of a fmap function still has this notion of latency, some time that I have to wait. It's an inherently composable abstraction, and you can use any number of layers that you want to. And you also can pass a few additional arguments if you need to. If your function, like compare, it accepts 2 arguments, not a single. In many cases, we have, in most cases, we have more sophisticated data. And here you see the example of nested data. I have this speaker with ID, with a name only. And I have this session with an ID, with topic, with number of slides, and with this reference to a speaker. And so how can I answer the question who speaks at this session just now? We know already how to get the speaker's name by the speaker ID. It's simple. To take speaker's name by the session ID, I have this another layer of indirection inside my data, and to do this, I have to use flat map functions. You can see it. And flat map function basically means the same as fmap, but it assumes that function that you passed will return not a value, not something that I can use just now, but it will return another intent to get more data, to discover more pieces of information that I need. Okay, all of that sounds reasonable, but how can I get result? So it's like interesting that I can manage with this fmap and flat map. To get result, I have to use this Muse run function, and Muse run will return you a core.async channel, and so you can read a result from this channel back. And it will analyze the whole tree of all operations that you passed, and it will choose the most efficient evaluation strategy for you under the hood. It also had this run with 2 exclamation marks variant that will block current thread until done. And usually you don't need this operation, but for tests, for demos like this, it's perfectly fine to use it. So, okay, what can it do for me? Why should I care? Or why do I need another layer of indirection, new abstraction to learn? So let's implement something practical. For example, number of common friends. And number of common friends is pretty common task for most social networks. It's like essential part of most of them. So we have this new data source, friends of, that will return us for given user ID some set of IDs of our friends. And what do I need to calculate number of common friends? First of all, to calculate number of common friends for user A and B, I have to fetch friends for user A, friends for users B, then apply set intersection function, and then apply count to the result of intersection. You can see this description with fmap. And let's run this. Let's see how Muse will do it. And as you can see on the screen, both requests for both users were sent simultaneously. And Muse is smart enough to do this for you under the hood, to understand that there is no reason for me to wait until I'll get friends of A to get the friends of B, right? This is something that you can do in your mind, but it's really hard for computers to understand this. Another thing, it's hard to imagine this situation in practice, but our implementation doesn't prevent us from doing this. And we can pass the same ID for both A and B. And in the most naive implementation, you will most probably fetch the same list for the same ID twice. But here with Muse, we see that it just skips for us redundant work, because it knows that, okay, it's the same piece of data. I don't need to call fetch twice. There are also many other examples, and the one that I want to show is friends of friends, which is also common for social networks. And what do I need to do? I have to fetch friends for given user ID, and then for each ID in sequence, call friends of again, and then just apply set union for all of them. And as you can see, there are two levels of executions. We call this friends of first time, then get back a sequence. And then for all operations in this sequence, we send requests simultaneously, because we know that these data pieces are independent. Okay, what if my data source implementation, I mean underlying implementation, like my data storage support batching, or for example, most of our microservices also supports batching, because this is a good way to deal with latency. And to tell Muse that you can find better way to execute multiple requests at the same time, you can use this batched source protocol with a single fetch multifunction. And here's an example of quite beautiful data jungling in Clojure. And what it actually does for us, it collects all requests grouped all together that can be run simultaneously, and ask if I can do something better than sending them all one by one. So you can see how it works. And the same example with just another declaration of friends of data source, and you can see that we sent only 2 requests instead of 4. Because we know how to deal with this batching. And this is really good way how you can reduce latency when you work with remote sources. So let's recap our example with timeline fetching. And this is just the same code that I showed you like few slides ago. And it used this Muse library facilities to declare data sources, but it's still clean and concise. And it looks pretty the same as naive implementation that we saw. And it's still, you can describe all, you can see description of all data pieces and all connections, right? And the most incredible fact about this code that it's actually free from all problems that we talked about. And if you will run this example, you will see that there are only three different stages or levels of executions. Muse will fetch for us this main timeline, this sequence of IDs. Then it will fetch all posts simultaneously at the same time. And then it will fetch users and user scores also at the same time. And it will deduplicate and just skip redundant work if some user was mentioned in the list of posts twice or more. So how did we achieve this? And it's really not that easy not that easy to answer this question. And I think that the key success factor is this nice separation of concerns. And the key idea that I use Muse to tell what do I want to do, what data I need, and what do I want to do with this data. And I use core.async to tell how do I need this data to be fetched. So Muse is a top layer abstraction, and core.async is low-level operations description. For example, how do I want requests to be sent, and what do I want to do with timeouts, and what do I want to do with retries, reconnections, and so on. And in most cases, I don't want to see these details when I'm reading code. I need this only when I have to solve some problem, but I just can avoid this. And another point here is that it's really generalized abstraction. So Muse doesn't have any notion, any ideas about concrete data sources that you use. You can talk to React, you can talk to Redis, you can talk to other microservices or Elasticsearch or Datomic or what do you want to do. This is like a nice layer of generalization. And of course, there are some known restrictions that you need to know about in advance if you want to choose this library to move on. And the first and the most like restricted one is that it assumes that your data fetches are side effect free, which basically means that you should not rely on the order of operations. And this is okay for most cases when you read data. If you will try to write data and then read it back, and Muse will run really heavy and aggressive optimization for you, and most probably you will fail, because this means that you are trying to modify some, not a global state, but some kind of super global state that lays on top of your application, and Muse library just don't have any ability to look into this state and to help you. Another thing, you need enough memory to store your fetches. And it also is really realistic assumption, but in some cases, if you don't have enough memory to store all information that you have to collect, you can use some tricks. For example, you can turn off caching for previous layers of execution if you know that you don't need this information anymore. But this is a trade-off between memory consumption and latency of all of your operations. And if you're sure that you will not have enough memory, most probably you should look into other approaches to solve this problem. For example, into streaming libraries or something like this. For example, if you need to fold huge sequence, you don't need to store all items from this sequence at the same time. And the next, Muse library uses core.async package, as you saw, to run fetches simultaneously and to deal with concurrency aspects. And This is only an implementation detail. And as far as Muse was born from real application and from real use case, it's perfectly fine to use core.async in our application with all of the information about execution context. But as a library developer, I really want to be less opinionated on this in future. So I will add some flexibility on this. So you'll be able to use any kind of concurrency primitive that you want to, or that you need to. There are also some ideas about future development cycle. This is not any kind of official roadmap. It's just few ideas that I'm currently working on. And the first on my list is better error handling. And there are two kinds of error that I want to deal with. And the first one is some situations when tree of your operation doesn't make any sense. And for example, in Haxl or in Scala, we can use type system to deal with these errors. But in Clojure, it requires some sort of manual work from me as a library developer, not for you, for sure. And the second kind of error that I want to deal with is exceptions that can occur from fetches, from your fetches. And I can't save you from yourself, but I can just try to help you understand what's going on and why. The next thing is debug mode. I want to add this functionality to pass special debug mode on flag into run interpreter that will trace all fetches and trace all latency just to give you ability to look inside and to check what's going on. And this is really helpful when you see some problems but don't understand why. The next part is applicative functors interface. It's a bit tricky, but just now, a library built on top of monad, the idea of monad. And the problem with monads that they are inherently sequential, right? If you have left and right side of computation wrapped in a monad, you have to evaluate left side and then pass the result of evaluation into the right side. This is an idea of monad. And I don't really need this sequential execution here. I want to be more flexible, and to give this flexibility, I can use applicative functors. Because you see, if you have function and arguments that are wrapped in the same containers, independent containers, I am free to evaluate both containers at the same time. I don't need to wait until function is evaluated before I'll start evaluating arguments. And this is really easy to do, but the hard part here is that I want this code to keep code in some shape of idiomatic closure. I don't want to turn your code into Haskell, obviously. The next item, this might look really strange for you. I want to get rid of fmap and flatmap functions. And the idea here that the tree of all of your operation is just a Clojure data structure. And you're free to choose what way do you want this data structure to be built. You can do this with fmap and flatmap functions. You can do this manually. You can send it over the wire, or you can read it from your disk, right, from the file. So I want to find better way how to express the idea of all of these data operations, and maybe I will end up with something that looks like Go macro. Maybe I will end up with something that looks like data log query. I'm not sure on this, but here is like a huge room for many experiments, and I'm exploring different, even crazy opportunities. And the last, but I'm sure not least, Clojure script support. I'm not really sure that there are too many cases when you need this functionality on your client-side application, but maybe. I've already got a few questions about it, so I will do. There's nothing hard to do here. The problem that I personally believe that if you need to talk from your client side to many multiple backends or different data storages, there are always better way for making some proxy on your server side, but it depends on your situation and your application. So I am looking for feedback, for any kind of feedback from adopters, and feel free to hit me up to talk about your systems and about your data and maybe about your ideas, how to solve the same problem, and do not hesitate to share what do you think on this, and stay tuned for more. Looks like